All right, this is lesson 1.3. We're going to be talking about transformations of functions and how those things appear on the graph, in the equation, and all of those sorts of things. So these are our objectives for today. We want to be able to identify a few different types of parent functions. We'll take a look at those in a minute. We're going to identify transformations of a parent function using both function notation and just their explicit equations. We're going to practice graphing some transformations on Desmos, and we're going to write transformations in terms of the parent function using function notation. All right, so let's go ahead and take a look at those parent functions we want to be able to identify. So a really quick glance, these are the 5 ones that we want to be able to kind of notice at a glance, either by the graph or by kind of taking a look at the equation. We'll go through each one of them in detail and kind of talk about naming them a little bit. So the first one is the linear function. Some people also call this the identity function. We have our, obviously, straight line. So if we're talking about a linear equation and a line graph, then we're going to be using this as our parent function. We have the absolute value function, kind of characteristic V shape. Anytime we have the absolute value of x in our function, we're going to be dealing with this one as the parent. We have the square root function, so right, looks kind of like half of a sideways parabola, has that very characteristic square root shape. Anytime we're taking the square root of x in there, this is going to be likely our parent function. We have the quadratic function, x squared in the equation. That's going to be our highest power of x is x squared. Then we're dealing with a quadratic, makes that parabola shape. And the last one we want to be able to identify is the cubic function. X to the third power is going to be our highest power, and then it has this kind of S shape or two-turn shape of the cubic graph. All right, so the first transformation we're going to be looking at are vertical and horizontal shifts. So first off, vertical shifts, if we are adding a constant onto the end of our function, then that's going to cause a vertical shift. Makes sense, I think, because if we simply take the original output and then add some number to it each time, that's going to cause the outputs to shift up some number of units, causing the entire graph to shift up that same amount. For this one, I'm going to be using an example as we go through. So let's just go ahead and use as our example function, we'll just do a simple quadratic. So our parent function we're looking at is the quadratic function. And let's say we wanted to create a graph that was a quadratic graph that was shifted up 3 units. Well, we would simply take our function f of x and add 3 to it. And that would look like x squared plus 3. Pretty simple. It's kind of added on to the end. Next thing we can do is we could shift the graph down by subtracting a constant onto the end of it. Same idea, we get the same output as the original, and then we just subtract some number from each time, and that would cause the graph to shift down. So let's say we want to shift that quadratic down, let's just say 2 units. We would do a -2 on the end. That would look like this. And then we can also do some horizontal shifts. These are a little tricky because they're a bit counterintuitive. If we want to shift the graph to the right some number of units, we are actually going to be subtracting a constant from the input variable. So that's going to be happening inside of our parent function rather than kind of just being onto the end. So if we want to shift our graph over, let's say 5 units to the right, we would do -5 to the input. So that's going to look like this. It's happening inside of the, inside of the quadratic function. It's happening inside of the squaring. It's happening directly to our input variable. That's going to cause a shift to the right. Now, the reason this is confusing is because subtracting, moving it to the right, that is a bit counterintuitive. We tend to think of movements to the right as being a positive movement, but we're subtracting. These horizontal movements are a bit counterintuitive. We have to keep that in mind when we're looking at these problems. Then if we want to shift the graph to the left, we're actually going to be adding a constant on the inside. So let's say we want to shift the graph 7 units to the left. we would go ahead and do x plus 7 inside of our function. So that's going to look like this, x plus 7 squared. And let's just go ahead and take a look at these graphs on Desmos here really quick. Let's exit this, clear what I have. But we'll just take a look at these graphs just quickly on Desmos. So our parent function being our basic x squared parabola, and we were doing some shifts. We wanted to shift it up 3 units, so plus 3 onto the end there, creating that graph. If we wanted to shift it down 2, I believe was what we did there, so we'll go ahead and shift it down 2. Yep, you can see that. We can also shift it to the right 5, minus 5. Yep, so that shifted the original one over 5. And then we went to the left 7, so plus 7. And you can type them in. If you type your parent function in there, you can type in the other function in terms of the parent function. So that's going to be useful. And so our original one, the parent one, is in red, and we can see all these shifts, right? Where we went up 3 units right here, where we went down 2 units here, where we went 5 to the right, and 7 to the left. So all of those functions are represented, creating the proper shifts that we were looking for. And I could also type them in terms of y as well. So if I wanted to go ahead and do this one as x squared plus 3, notice it's the same graph that we had there. Or if I wanted to write this one, y equals, x, parentheses for that one, x minus 5 squared. Notice it does still create that shift to the right 5. I kind of zoomed out, but you can still see how it shifted the original graph over 5. Or I could even call it a different function name. I could call it g of x as well if I wanted to make it different. I don't want to use the same function notation. I don't want to call it f because I already have a function named f. So just make sure we're changing the name if we are going to write it out in its actual equation form. All right, so I'm going to go ahead and leave that. I'll leave it up. So we're going to go back to presentation here and kind of look at some examples, see if we can identify these different types of shifts. So here we go, we have a function g of x equals x minus 4 in parentheses to the 3rd power. We need to identify what is the parent function that we're working with here. And so I can see it's to the 3rd power. That's going to be our highest exponent power. So our parent function is going to be the cubic function. We'll call it cubic. And then we need to kind of examine what's happening. How did the parent function get changed? And what I'm noticing is we're subtracting a 4, a constant 4, and we're doing it inside of the cubic function. So whenever it's done on the inside of the function, that's going to be a horizontal shift. Remember, horizontal shifts are a bit counterintuitive, right? Minus is actually to the right. So it's going to be 4 units to the right. If we needed to, we could graph this and our parent function on Desmos and just take a look and make sure that is what's happening. The other thing I want to do here really quickly is talk about how I could write g of x in terms of f of x. So I could say that g of x is equal to some transformation of the function f of x. So in this case, we shifted it to the right. It was f of x minus 4 on the inside. So our function g of x, written in terms of the parent function, would look like this. We took the input, subtracted 4 from it. So that's something that we can do. We can write one function in terms of another one. And I'll do that a few times here as we go through the examples. Okay, let's go ahead and take a look at the next one. So this one here, as I'm looking at it, we can see that we have a square root function. G of x is equal to the square root of x plus 5. So our parent function would be our basic square root function. And notice the constant that we've added this time is not inside of the square root. It's not inside of the square root function. It's to add it onto the end. So that's going to represent a vertical shift, either up or down. And the vertical shifts work the exact way we might think. Adding is up, subtracting is down. So this one has moved 5 units up. That's how it's been shifted. And again, I can write g of x in terms of f of x, right? So I'm going to go ahead and do that. G of x is equal to our function f of x, right? Same thing, it's got the same square root, but then what we did was, well, we added 5 onto the end of it, representing that shift upwards of 5 units. So that's how we can write our function g of x in terms of the parent function that we identified, the square root there. And one more example of this. All right, so now we can see here g of x is equal to the absolute value of x plus 2 minus 7. So our parent function, in this case, is the absolute value function, because we're taking the absolute value of x here. In this case, I can see 2 things that were either added or subtracted. So 2 constants that are being added or subtracted into our function. First off, we have this plus 2, which is happening inside of the absolute value, which will represent a horizontal movement. And we have this minus 7 on the outside after the function, which is going to cause a vertical movement. So there's 2 things here. So we're moving 2 units to the left. Remember, on the inside, it's a bit counterintuitive. Plus is to the left. And minus 7 on the end means that we're moving 7 units down. So our graph, our regular absolute value graph, we have a XY axis here. It's going to move from being at the origin here, it's going to move to the left and down. And it'll be somewhere over here, right? Counting the units appropriately and everything. All right, so now last thing, let's go ahead and take a look at how we could write g of x in terms of f of x. So g of x is equal to, now we're doing 2 things. We're shifting it to the left, so that needs to happen inside of my function. So f of x plus 2, we added that on the inside of the function. And then we have a vertical movement, so we need to do that onto the end of the function, minus 7. So that's how we can write our function here up top, g of x, in terms of the parent function that we just identified. All right, we're going to go ahead and move on to some different types of reflections that we can do. All right, so there are 2 reflections that we're going to be looking at. We're going to be looking at how we can do a reflection across the x-axis and a reflection across the y-axis. It really just has to do with where we're applying a negative value, right? So whether that negative is happening outside of the function, applying it to the entire thing, distributing it if necessary, or whether we're applying it directly to the input variable. They're going to cause a different reflection. This one is going to cause us a reflection across the x-axis, right? We're going to flip our graph from maybe up above. We could have a parabola up here. And it might flip to be down below the axis, right? It would flip like this. Most of our graphs, because we're dealing with functions, are not going to be symmetrical across the x-axis, so this type of reflection will always do something. Whereas if we have a reflection across the y-axis, notice how this parabola might not change at all. Could, but it might not, depending on where the parabola is positioned, right? And then if we have a reflection across the y-axis, like this is doing on the inside, right? Our y-axis is up here. Say we had an absolute value graph, something like that. If we reflect that across the y-axis, right, we'd end up with a graph that looks something like this, flipping in this direction horizontally here. Let's go ahead and just do a quick example here of both of these types of reflections. So let's say we're dealing with a simple, let's just do the square root function. So if we want to do a reflection over the x-axis, we're going to need to apply a negative to our whole function. So that's just going to be a negative in front, square root of x. If there were more terms to this, I would make sure to distribute that or even put parentheses around my function and make sure I distribute to everything that's involved in it. But in this case, there's only one object, so I don't even need to bother with that. And then if we want to do a reflection over the y-axis like this, what we would do is this. We would apply a negative inside of the function. So it would be the square root of negative x. And that would cause this type of reflection, almost exactly like this. We'll take a look at some graphs on Desmos here with some of our other examples. All right, I'm going to go ahead and move on and look at examples of these reflections, see if we can identify them. Okay. So here we go. We have a function g of x, which is negative, parentheses, x minus 4 squared. So our parent function in this case, we're raising it to the second power, so that's a quadratic function. We'll go ahead and call it f of x. That's a quadratic. And then there's two things happening. So this one we might notice from the previous section is it represents a shift, a horizontal shift. But what we're really looking at here is what's the reflection. So where are we applying a negative? In this case, the negative is not being applied inside, it's being applied to the outer part of the function. So in this case, when it's applied on the outside, that's going to be reflecting it up and down. And so that's going to reflect it across the x-axis. X-axis. And we can go ahead and write this function here in terms of our parent function as well. So I'm going to go ahead and do that. So g of x equals, so what are we doing to this function? Well, if we're applying a negative to the outside, we'll go ahead and put a negative in front of it. And we're subtracting a 4 inside of our function here to cause that horizontal shift as well. So those are the two things that are going on, and that's how we can write this function in terms of the parent that we just defined right there. And let's just go ahead and take a look at what that might look like on Desmos. I just want to show the reflections on the actual graphing program. So I'm gonna leave this for a second and go back to Desmos. All right, so our function g of x, I'm gonna go ahead and close these, get rid of them, was x minus 4 squared. Okay. Oh, there was also negative, but we can actually just do it right here. So there's no negative applied, and if I put that negative in there, watch how it changes the graph. Flipped it to be down here, right? Or I can even copy this function and compare it. Just go ahead and make another color. So this one, the blue one is without the negative and the red one is with the negative. So we can actually just sort of directly see how that negative is affecting our graph. It's causing that reflection up and down across the x-axis. Okay. All right, well, let's keep going here. All right, we just did that. So now, example number 2. So we have our function g of x, which is the square root of negative x plus 2. All right, so we want to identify the parent function. So in this case, we are talking about a square root. So we're doing with the square root function. That'll be our parent. I'm not going to write that out, square root. I can again see two things that are happening. Mostly we're focusing for this example, we're focusing on the reflection, but there's also the plus 2, right? Remember, plus 2 is going to cause us to go up 2 units. It's happening on the outside of the function onto the end. But how is this negative happening? We need to identify, is it inside the function or outside the function? And in this case, it's inside. So that's going to cause a reflection across the y-axis horizontally. So it's going to reflect over the y-axis. Right, so it's gonna cause that graph, I guess, which is also shifted up 2 units. So that square root graph that's right here, it's going to flip it across the axis. And so it's going to be going this way. Same shape, but reflected over there. And that's how that negative is going to apply there. Last thing I want to do is what I've been doing all these, just write g of x, write this function in terms of the parent. So g of x is equal to f of negative x, again, because we're applying that negative inside of the radical, and then plus 2 on the end, because that plus 2 is just being added onto the end. Pause for a second in case people are copying down. All right, now, final example here of the reflections. So looking at this one, we have g of x is equal to negative x plus 5 to the third power. So to the third power, that's going to give me the type of function I'm dealing with, what parent function I want to have. So this is a cubic function. There's a lot going on with this one. With the negative and the plus 5 happening on the inside, this can be actually quite tricky to identify what's happening and the order. Because remember, this negative on the inside is supposed to be a reflection over the y-axis. And this is supposed to be a horizontal movement to the right. Oh, my fault, not to the right. To the left. Remember, the movement on the inside is a bit counterintuitive, and this will be down. But really, what's happening between these two is the tricky thing, because reflecting horizontally and moving horizontally, the order that these two things happen is very important. Right now, we're just going to identify what all the transformations are happening, so to our basic cubic function. So there's 3 things, right? I'm not saying them in order. This is not an order right now. We might need to do some further investigation, but there's a reflection over the y-axis. There is a shift to the left 5. And the third thing we identified there is it is going down 1. I'm actually going to go ahead and take a look at this equation in Desmos, and this will be the end of part 1 after I do that. So I'm going to go ahead and clear this so I can go over to Desmos. I've got to remember that equation. I think I got it. Negative x plus 5 to the third power minus 1. Okay, and I'll put my parent in there. Equals x to the third. All right, so I can see how it was reflected horizontally, right? Because the original, the parent here that's in blue, is down on the left and up on the right, but this one is opposite of that. It's been flipped. It's up on the left and down on the right. You can also see it actually kind of appears shifted to the right, which is odd because, you know, the plus 5 actually is to the left. But we'll kind of, I think we'll see how that's happening here in just a second. And then this minus 1, I can see maybe specifically this point, how it's shifting down 1 unit to be right here. Yeah, minus 1. At 5 minus 1. Okay, so if we think about these 2 things that are happening on the inside, if we do it in this order, if we move it to the right 5 first, so if I do that, plus 5, and then flip it over, it's going to actually look like that movement was actually a movement to the right, because now that we've moved it to the left, sorry, I think I misspoke. After we moved it to the left, now we apply this reflection, we can kind of see how it's going. The other thing that can happen here is if you kind of factor this negative out and you end up with a negative negative, like if I were to distribute that back in, it would end up being the same thing. You can see a little better how it's happening. We actually moved it to the right and flipped it horizontally. These are tricky, and I'm not going to ask us to get too bogged down in the details of this, but understanding and seeing how they happen and messing around with them on Desmos can be very useful to figure this out too. All right, I'm going to go ahead and stop this video here. I'll pick up another one to finish off this lesson. So see you again in part 2.